Hello everyone, let's come to the section 4, Applications of Interpolation. The first subsection, we consider numerical integrations and the degree of accuracy. So, the topic of this subsection is about the numerical integrations. In calculus, we have learned the Newton-Leibniz formula that we know the integral of a function fx on an interval ab can be obtained by the capital FB minus capital FA. It's okay? Well, capital Fx is a primitive function of fx. For example, if fx equal to cosine x, then we know it's a primitive function. Capital Fx is sine x. 1. Of course, the primitive function is not unique, so we can consider plus a constant c, right? Okay, by the difference between the two function values, c is disappear, right? So we can just use sine x as the primitive function. It's okay? So, now you see, the left side is integral. The right side only with two function values. Of course, we know integrations or integrals are very important issue in calculus. In many applications, we need to compute the integral for some functions, right? Okay, now but in some applications also we don't know the function representation, the expression or the formula of function fx, or maybe it's more complicated. We cannot use the Newton-Leibniz formula directly, so we need to consider the numerical integration. So here, in many cases, it is difficult to use the Newton-Leibniz formula. Okay, for example, maybe capital Fx, the primitive function, cannot be represented by elementary functions. For example, okay, Fx equal to 1 over ln x, or sin x over x, or the exponential function of minus x squared, or 1 over 1 minus k squared sin x squared. For these functions, we cannot represent their primitive function by some elementary functions. Okay, we know this fact in calculus, right? Or maybe more difficulty, fx cannot be represented implicitly. We only know some discrete data. Okay, for example, we just know some discrete points of a function. Then we suppose here we have a curve, right? A function fx, but we don't know its formula. So we also want to approximate the integral. Integral means the area. It's okay? So, numerical integrations. Okay, and also maybe even we know the primitive function, but it is very complicated. Okay, for example, this function, okay, is a primitive function like this. Very complicated, right? So it is also hard to use Newton-Leibniz formula. So we want to use numerical method to compute the integrals. This is the topic of this section. Now, let fx be an integrable function on interval ab. We consider its integral denoted by if, integral of f denoted by integral of fx on the interval from a to b, okay? And the numerical integration is to use the weighted summation of function values like this, denoted by INF. Okay, the summation k from 0 to n, ak multiply fxk, where ak are some coefficients and xk are some knots. We use this summation to approximate the integration. Then this is numerical integration. Why we can use this formula? Actually, now you see, for the Newton-Leibniz formula, we know we can obtain the integral by several discrete function values. Of course, here we use primitive function capital F, but now we only need to use the function values of fx at some knots xk. Here we use n plus 1 knots. So this is our aim, to use this numerical integration to approximate the exact integral. It's okay? So we use INF to approximate IF. So the question now, how to choose the knots xk and how to determine the coefficients ak or weighted summation. So this coefficients also called weights, okay? Okay, the equation we call a numerical quadrature. Quadrature means one-dimensional case. For two-dimensional case is curvature. Of course, in our course, I only introduce you the numerical quadrature for the one-dimensional case. Okay, one-dimensional function. INF, okay, is the summation of ak multiply fxk, where the constants ak independent of fx are called weights. That means you can change the function values, but you don't change the coefficients. The coefficients are fixed for one formula, and xk are called knots or nodes. Okay, here knots we know by interpolation method. We know the knots, right? Okay, so here the background of numerical integrations. Actually, by the mean value theorem for integrals, we know this formula in calculus. The exact integral of fx on interval ab equal to f c multiply b minus a. Remember, this is the mean value theorem for integrals. But the question is, we don't know where is c. We only know c lie in the interval ab, but we don't know its exact location. Okay, but here, by this formula, we know we can just use one function value to obtain the exact integral, and b minus a is a constant. Okay, so here that means we just use one node c, but we don't know where is c, the problem. Okay, but we can explain this formula in geometric meaning like this. Here is the coordinates, and suppose this is a graph of the function fx, the curve, right? Then we know the integral of fx on the interval ab means the area of this part below the curve, right? The area is the integral. And this formula means there is a point c. For example, here is a c. Then we can just use the area of this rectangle domain, right? Now you see, this is the rectangle domain. So the length is b minus a. The height is the function value fc, So height multiplies the length is the area of this rectangle domain. That means we can just use the area of the rectangle domain to obtain the area below the curve. It's okay? So this is the geometric meaning. So here, the area of the rectangle f c multiplied b minus a equal to the area of the curved trapezoidal. Okay, we call this shape by curved trapezoidal. That is the integral. Of course, we cannot use this formula. This formula is a theoretical result because we don't know where is c. So in applications, we cannot use it. We need to find other useful, effective formula. Now, we want to use the following ways to obtain numerical quadratures. Here, the equation means the area is exactly equal to the area of the rectangle. So if we can accept some error, then we can choose a simple rectangle to use its area to approximate the integral. So this is the idea. It's okay for you? Now you see, if we just choose the left value, function value, I show you this figure. Now this is fx. Because we don't know where is the exact c, so we choose a simple c. Now we just choose the left endpoint a to use fa as height, so we can obtain a rectangle like this in red color. So its area is the height fa multiplies the length b minus a. Of course, this area is not exactly equal to the integral. So here we use approximation. It's okay for you? However, we can just use this left area of the left rectangle to approximate the integral. Of course, maybe the error is big, but at least we find a way to approximate the integral, right? Okay, so we call this by the left rectangle rule. Of course, you can choose other point. For example, we can choose the midpoint of the curve of the interval. So here, again, we don't use left end. We use the midpoint. So here, 2a plus b over 2. We use the function value f at a plus b over 2 as the height. Then we can obtain, okay, here, the area of the rectangle. The height multiplies the length, right? Then we call the rule by middle rectangle rule. Now you see, the height of the midpoint multiplies the length. Of course, you can choose another one. For example, the right end point, fb, as the height to multiply the length of b minus a. Of course, you see, in this case, the error is big, right? The error is big. Okay, this is the right rectangle rule. It's okay for you? Now we only use one point here. We just use one point. Of course, it is not good enough, right? Maybe someone will think, why don't we use trapezoidal? Another trapezoidal like this. Now you see, I draw the figure here. We can choose the trapezoidal. We use both endpoint fa and fb. When we connect the 2 points, we can obtain a rectangle or a trapezoidal. Then we can use the trapezoidal, the area of this trapezoidal, to approximate the integral. Now, the area of this trapezoidal should be fa plus fb over 2 multiply the length b minus a. It's okay? This is the area formula for trapezoidal. That's okay for you, right? And of course, we can find this rule should be better than the rectangle rule. It's okay for you? Of course, I will explain you how to determine the accuracy. But in geometric, we can find the trapezoidal rule should be better than the rectangle rule. It's okay? Firstly, we find a way to approximate the integral by some function values. So here we have the problem. Where are the nodes? Here we choose different nodes, right? It's okay? Left end, midpoint, right end, or we use both nodes, FA and FB. Okay, now you see b minus a over 2 here, the coefficient b minus a over 2 is independent of f. You can use change function f, but the coefficient is fixed. Now, these coefficients are b minus a. They are fixed, right? It's okay? So this also some numerical quadratures. Is clear? Okay, let's continue. Now, generally, we can construct the interpolating quadratures by using the interpolation polynomials on the equally spaced nodes or equally spaced nodes. Okay, also we can use nodes. Okay, so that means we subdivide the interval AB equally into n subintervals by the step size h equal to b minus a over n. It's okay? So then we can obtain the nodes, or actually they are interpolating nodes by xk equal to a plus k multiplied h. It's okay? So here, I write here. So here is a, here is b. For example, if n equal to 2, that means we obtain 2 equally subinterval, right? Then we choose x0 equal to a. It's okay? When k is 0, just a. And x1 is the middle point, so a plus b over 2, right? And b is the end point, so it is x2, right? Because n equal to 2. So h is the step size b minus a over 2, right? Because here n equal to 2. See? Of course, if n is 3, then we use x0, x1, x2, and x3, and so on. It's okay for you? These are equally spaced nodes or nodes. Now, we consider the fx, the integrand function, can be represented by the interpolation polynomial and the remainder term. We have learned this result in section 2, right? Okay, so we know we can just use Lagrange, for example, Lagrange interpolation formula to obtain a polynomial to approximate the function fx with the error term or remainder term denoted by Rnx. So here, now you see, here fx, k are the function values, discrete function values at the nodes xk, and multiply the basic functions, the Lagrange interpolation basic functions, LKX. So you should remember how to obtain LKX. It is a ratio, right? LKX is a ratio, and numerator are some product, and denominator also some product. Okay, replace x by xk and so on, right? So I don't write it in details. Okay, now that means we can use the polynomial to approximate fx. Of course, we can use the integral of the polynomial to approximate the integral of fx. So the integral of fx equal to the integral of this polynomial, right? And plus the integral of the error term or the remainder term. It's okay? Then now you see, because fx, k are some function values, so we can change the order between integral and summation. So we can compute integral firstly, and because fx, k are constants, so we just consider the integrals on lkx. So here we compute lkx, the integrals, that multiply function values fx, k. And because lkx, we can obtain lkx just determined by the nodes xk. It's okay? Here, xk minus, okay, I write it. xk minus x1 multiplied to xk minus 1. And, oh, sorry, the numerator should be x. Okay? And x minus other nodes, xk plus 1. Then multiply to x minus xn, right? And denoted and divided by, replace x by xk, right? It's okay? xk minus 1, xk minus xk plus 1, xk minus xn, right? It's okay? This lk. Now you should remember, lk, the basic function, is determined by nodes. So there is no f. There is no f, right? So that means the integral of f of lkx, if we denote for each interval or integral of lk by ak, then ak is independent of f. It's determined by xk, right? So, and also we know the remainder term, the error. So that means if we replace or represent the polynomial by Pnx, that means we use Pnx to approximate fx by the Lagrange interpolation method. Then we can use the integral of polynomial function, integral of polynomial Pn to approximate the integral of fx, right? And then we can Pn just by the summation of ak multiply fxk. What is ak? Ak is the integral of lk of each Lagrange interpolation basis. It's okay? Basic function, okay? So here we just use the interpolation polynomial to construct the numerical quadrature or numerical integration formula. It's okay? So that is the application of interpolation. Okay, so here we can write the numerical quadrature by ak multiply fk and compute the summation. It's okay? Okay, then we just take this part by INF. So denoted INF by the sigma k from 0 to n ak multiply fxk. Then we call this formula by the Newton-Cotes formula on n plus 1 nodes. Okay, xk, x0, x1 to xn. And the weights ak can be obtained by the integral of lkx. Okay, so next we need to compute ak for specific formula. That means we need to consider different n to obtain different formula. different formulas. It's okay for you? But you should remember how to construct this formula. We use equally spaced nodes. So that means xk equal to a plus k multiply step size h. So it is a plus k multiply b minus a over n. Right? It's okay? H is a step size. And also we know the area of the quadrature is denoted by ENF. It is just the integral of Rnx. And in section 2, we know the remainder term. Rnx can be obtained by the n plus 1's order derivative of f at some c. This c is depended by x. So here we use subscript x to represent c depends on x, right? Okay, divided by n plus 1 fraction number and multiply wn plus 1x. Okay, remember wn plus 1x is x minus x0 multiply x minus x1 multiply to x minus xn. Okay, so we also know the error term for the Newton-Cotes formulas. Clear? This is a general idea. Okay, now let's practice. We start from n equal to 1. N equal to 1, that means we only use 2 nodes, right? So we denoted by I1F. We only have 2 nodes. 2 nodes in the interval AB. Of course, we just choose the 2 endpoints, right? Endpoints. So FA and FB. Clear? X0 and X1. So we only need to determine the 2 coefficients A0 and A1. It's okay? So what is A0? We know A0 is the integral of L0x. What is L0x? Remember, this is the linear Lagrange interpolation basic function, right? So it should be x minus b over a minus b. Remember? Because here that means x minus x1 divided by x0 minus x1. It's okay? x0 is a, x1 is b. It's okay? Okay, it is easy to compute the integral. You will obtain b minus a over 2. Right? It's okay? Actually, we can obtain it easily because we know the figure. Actually, we can obtain it easily because we know the figure should be like this. This is L0x, right? This function value is 1 because when x equal to a, then a minus b over a minus b is 1. When x is b, b minus b is 0, right? So we know this area, the area of this triangle should be b minus a over 2, right? Because the height is 1. The length is b minus a, so the area is height multiply length over 2. It's okay? This is just the area or the integral. It's okay? And also we can obtain a1. a1 is the integral of L1x. So L1, this is L0x, then we know L1x should be x minus x0 over x1 minus x0. It's okay? You should master the formula of Lagrange interpolation basis, right? Okay, so x minus a over b minus a. Of course, it's figured like this, right? This is also function value is 1. This is L1x, right? Okay, so its integral just the area of this triangle. Of course, it is same as b minus a over 2. It's okay? Of course, you can directly compute the integral. Let's show you compute. Okay, here we know by the Newton-Leibniz formula, we should know its primitive function is x minus a square over 2 multiply b minus a. It's okay? This is a primitive function. Okay? A and b, the function value of b minus the function value of a. It's okay? So here, when x equal to a minus a is 0. So only when x equal to b. So b minus a square over 2 multiply b minus a. Of course, it's just b minus a over 2. Right? It's okay? We obtain the weight a1. Of course, it is similar to obtain a0 by b minus a over 2. Then, okay, we know this is just the trapezoidal rule. So I1f equal to a0 equal to a1 just b minus a over 2. b minus a over 2 multiply fa plus fb. Okay, so actually this is just the trapezoidal rule. Let's come back here. Now you see this formula: b minus a over a multiply fb plus fa plus fb. It's okay? So that is why we call this by trapezoidal rule. Okay, actually by the figure, you see what it means, the trapezoidal rule. Actually, we obtain I1f because I1f is actually the integral of P1x. It's okay? Because P1 is a linear Lagrange interpolation polynomial. Like this here. It's okay? So what is P1? Actually, P1 is just the straight line, right? Here, I write here. This is the figure fx. And this is fa. Here is b, right? What is P1? P1, that means we just use 2 points to obtain a linear polynomial or straight line, right? That means we use this straight line. This is P1x. So we just use the straight line to approximate the curve of fx, and we use the area of this trapezoid to approximate the area of the curve. It's okay? The integral of the curve. So that is a trapezoidal rule. So we use different view, the geometric view and the Lagrange interpolation view to explain the trapezoidal rule. It's okay for you? Clear? Of course, you should remember well this very famous formula, trapezoidal rule. Okay, that means we can just use 2 function values of function fx to approximate the interval. So that means we can use b minus a over 2 multiply fa plus fb to approximate the integral of fx. It's okay? This is a famous trapezoidal rule. Okay, next, in order to improve the accuracy, now we choose n equal to 2. That means we have 3 nodes, right? Okay, I explained you before. Then n equal to x0, and the endpoint is b, right? So we choose x1 as the middle point, b minus a, x1. So here, x0, x1, and x2. It's okay? We have 3 nodes or nodes. And now we only need to determine the 3 weights or coefficients, a0, a1, and a2. Okay, now let's continue. a0 should be the integral of L0x. But you should know, here L0x should be the quadratic interpolation polynomial. It's okay for you? Remember, I write here, L0x should be x, follow me, please follow me, x minus, because the index is 0, so should minus other nodes, so minus x1 multiply x minus x2, right? Divided by, replace x by x0 minus x1, x0 minus x2, right? You should very quickly to write the basic functions, right? L0x. Now you should know x1 is a plus b over 2. Oh, sorry, here should be b plus a plus b over 2. Sorry, the midpoint a plus b over 2. Here, okay? So x1 should be a plus b over 2. Okay, multiply x minus x2 b, right here, divided by x0 is a, so a minus a plus b over 2 multiply a minus b. It's okay? So you can please check, okay? You can compute, because this is just a quadratic polynomial, so it is easy to compute the integral on AB. You will obtain this result, b minus a over 6. Please check after you finish this video, okay? I omit the details. So this is A0. And next, we need to compute A1. A1 is the integral of L1x. And you should remember how to write the L1x, right? So I help you to write here. Please follow me. Again, we practice. Okay? Index is 1, so numerator x minus other nodes, so x0, x minus x2, right? x2. And then replace x by 1, so x1 minus x0, x1 minus x2, right? You should remember this formula. This is L1. So here, x minus x0 is a, x minus x2 is b. So divided by, replace x by x1, x1 is midpoint, a plus b over 2 minus a plus b over 2 minus b. It's okay? Also, please check, you can obtain the integral of this polynomial. The result is 2 multiply b minus a over 3. Okay? Okay, actually, you can remember it by 4b minus a over 6 by the same denominator. Okay? And also a2. a2 is the integral of L2, right? So what is L2? Okay, practice again. Okay, index is 2. So the numerator should be x minus x0 multiply x minus x1, right? And replace x by x2 minus x0, x2 minus x1, right? It's okay? Okay, now you see, x0 is a, x1 is a plus b over 2, then x2 is b, b minus a plus b over 2, right? Okay, we obtain this quadratic polynomial. Okay, and I also ask you to practice the integral. The integral of this function is b minus a over 6. b minus a over 6 equal to a0, Okay? So here we obtain the 3 coefficients or weights, a0, a1, and a2. Okay, actually I should remind you, if you y a0 equal to a2, if you remember the figure, okay, here, I directly draw here. Here is 1, the function value is 1. And for L0x, okay, it has 2 0 points at x1 and x2. So it's a figure like this, right? The parabolic curve like this. Remember, this is L0x. And what is L2x? L2x has two 0 points, x0 and x1, and at x2 its function value is 1, so its figure should be like this. Okay, now you see, because the x1 is midpoint, so this figure is symmetric to this figure. It's okay? So the area means this area, right? And the integral of L2 should be this part, this area, and this area, right? Now you see, they are symmetric. They are symmetric. Of course, that means the integral should be same. The area should be same, right? So b minus a over 6, b minus a over 6. The midpoint, the middle weight a1 equal to 4 over 6 multiply b minus a. Okay, you should remember 1, 4, 1 over 6, right? Okay, 1 plus 4 plus 1 equal to 6 equal to the denominator. Okay, in our conclusion, we can obtain this is very famous Simpson's rule. So denoted by I2F. It is b minus a over 6 and 3 coefficients 1, 4, 1. Okay, 1 multiply fa plus 4 multiply f midpoint a plus b over 2 plus fb. Okay, so we can use this formula to approximate the integral of fx. We use 3 function values. Okay, you should remember the 3 weights 1, 4, 1, and the denominator is 6 because 1 plus 4 plus 1 is 6. And don't forget, you need to multiply the length of the interval b minus a. Clear? This is very famous and very popular Simpson's rule. Okay, let's show you the geometric meaning. For the trapezoidal rule, this is fx. Okay? By trapezoidal rule, that means we use P1 straight line to connect the 2 points to obtain a straight line. Then we use the area of this trapezoidal, right, to approximate the area of the curved trapezoidal fx. So this is okay. I clean here. This is a trapezoidal rule. Next, let's consider the geometric meaning of the Simpson's rule. Now, for Simpson's rule, we use 3 function values at 2 endpoints and also the midpoint, right? So that means we use the 3 points. We draw a parabolic curve, interpolates the 3 points, right? We obtain P2. Then we use P2x to approximate fx. Of course, we also use the integral of P2 to approximate the integral of fx, right? So we use this area, right? This area of this parabolic curve to approximate the area of the fx, right? Okay, now of course, if you compare these 2 graphs, you can find by P2 is better, right? We use this area more better than use the straight line, trapezoidal rule. So Simpson's rule should be better than the trapezoidal rule. It's okay for you? Okay, so the general idea is we use the Lagrange interpolation polynomial Pnx to approximate fx. So we can also use the integral of Pnx to approximate the integral of fx. So then we denote the integral of Pn by INF. Then INF is the Linear combination, linear combination of the function values. Clear? Okay, let's consider another case when n equal to 4. Okay, maybe you will ask why we don't consider n equal to 3, because for Simpson's rule, n equal to 2, right? Because we have 3 nodes. Okay, I will explain you later. Now, let's practice when n equal to 4, then it's the Cotes rule. So, denoted by I4x, I4FF, I show you the results directly. I omit the details. Okay? So, let's consider, because we use n equal to 4, that means we use 5 nodes, right? A, B, and midpoint and quarter point, right? So here, A equal to x0, this x1, x2, x3, and x4. It's okay? x0 is A. Now you see FA, fx1, fx2, fx3, and fb, right? And you should note the 5 coefficients: 7 symmetric 7, 32 symmetric 32, 12 the middle one. Okay? And the denominator is 90. You can try. You compute the summation: 7 plus 32 plus 12 plus 32 plus 7. Okay? So that means 2, 7, 14, right? 2, 7, 14. And 2, 32, it is 64, right? 64. And plus 12, right? It's okay? So now you see 4 plus 4 plus 2 is 10. 6, 7, 8 plus 10, so 90. Right? It's okay? So your orbital, the denominator is 90. Okay, so here I just show you that means the summation we have a good property. And don't forget we need to multiply the length b minus a. This is the Cotes rule. Okay? And now actually we know some properties of the weights of the Newton-Cotes formula. Since the Lagrange interpolation basis on equally spaced nodes are symmetric and satisfy the partition of unity. Do you remember what it means? The partition of unity means the summation k from 0 to n lkx equally to 1 is equals to 1, right? Remember? The summation of lkx equal to 1. Now, the integral of each lk is ak. So, we can obtain the summation of all weights ak, k from 0 to n summation, right? Each ak is the integral of lkx. And we can change the order, right? We can change the order of summation and integral. So we can compute the summation firstly. And here, remember, we know the summation of lk equal to 1. Then the integral of 1 is just b minus a. So all the summation of all weights of ak should be b minus a. So that is why here now you see all the coefficients, the summation is 90 over 90. So b minus a. Okay? And also here 1 for 1, 6 disappear, b minus a. It's okay? And also here when n equal to 1, b minus a over 2, summation is just b minus a. Okay? See, this is also unit partition of unity. Clear? But here the unity should be b minus a, because with the length of the interval. It's okay? Okay, at last, let's practice by 2 examples. The first example, let's compute the integral by the trapezoidal rule and the Simpson's rule respectively. Okay, so the integral is 1 over 1 plus x. Okay, the integrand function, the interval from 0 to 1. Of course, because we need to also check the accuracy, so we can compute its exact integral. The primitive function should be ln 1 plus x. It's okay? Because ln x, the derivative is 1 over x, right? So here, 1 plus x as the denominator and the derivative of x is 1. Okay? So, now, by the Newton-Leibniz formula, when x equal to 1, then here should be ln 2. Minus when x equal to 0, ln 1. Right? Okay, now you can obtain the result should be 0.693147. You can use your calculator to obtain this number. Okay? This is exact integral. Of course, it should be of course float number, right? We use 1, 2, 3, 4, 5, 6 significant digits. But here, because now we don't consider round-off error, we consider the error by the formula. Okay, so here, we use this number as exact value. Okay. Now let's use trapezoidal rule, numerical quadrature, or numerical integration rule. Okay, so firstly you should remember how to use trapezoidal rule T. Okay, it should be b minus a over 2, the length over 2, right? Multiply fa plus fb. It's okay? This is trapezoidal rule. Then b is 1, a is 0, so 1 over 2 multiply fa. Fa means when x equal to 0, so it is 1, right? When x equal to 1, it should be 1 over 2. 1 over 2. Okay, that is very easy. Okay, we know the result is 3 over 4, right? 3 over 4, it is 0.75. Okay, so that means we can use 0.75 to approximate the integral of 1 over 1 plus x, right? We know the exact value is 0.69 and so on, right? But here, we just use 0.75 to approximate the integral. Okay? It is very simple, right, to use the trapezoid rule. Of course, we can see the error is a little big, right? So, in order to improve the accuracy, then we can use the Simpson's rule. Now, let's try. We use capital S to represent the Simpson's rule. So you should remember the formula, right? b minus a over 6, 1 for 1. Okay? fa plus 4 times fa plus b over 2 plus fb, right? Okay, so b minus a is 1, so 1 over 6, right? fa, we're here. fa is just 1, right? So 4 times fa plus b over 2. a is 0, b is 1, so 1 over 2, right? So when x equal to 1 over 2, then it is 1 over 1 plus 1 over 2. It's okay? So here should be 1 over 3 over 2. So it is 2 over 3, right? So 4 times 2 over 3. So it is 8 over 3. Right? It's okay? So this is 2 over 3. And plus FB here we already know 1 over 2, 1 over 2. Right? It's okay? So you can know the summation is 25 over 36. So it is equal to 0.694. Okay, now you see 694 693. At least we have 2 significant digits, right? But here 7 and 5 is with big arrow, right? Of course, we only have 1 significant digit, 7, right? Because here 6, 9. Because if you only use 1 significant by round up, it should be 0.7, right? Okay, so now I show you the Simpson's rule is better than the trapezoidal rule. It's okay? Of course, here I don't use the theoretical analysis to prove Simpson's rule is better than trapezoidal rule, but now for the numerical example, we know, okay, Simpson's rule is better because we use three function values. Trapezoidal rule only use 2 function values. It's okay? Okay, so this is example 1. Let's practice example 2. We compute the integral by the trapezoidal rule and the Simpson's rule respectively. Okay, we consider this integral. Okay, the integrand function is exponential function of minus x squared. Okay, so in the beginning, here, now you see, here we just said, for this fx integrand function, we cannot find its primitive function by elementary functions. So, in this example, we cannot use Newton-Laplace formula, right? This is a counter example. Okay, so here we have to use this numerical integration. It's okay? And also I can show you, okay, this integral is almost to 0.74684. A good approximation. Now let's try. We use this number to compare the numerical results by trapezoidal rule and Simpson's rule. Okay? So again, by the trapezoidal rule, so we can use b minus a over 2 multiply fa plus fb, right? Okay, b is 1 minus 0, so 1 over 2 multiply fa. When x equal to 0, then it is 1. When x equal to 1, then it is e minus 1, minus 1 power, right? Minus 1 power. Okay, so you can use your calculator, then you will obtain 0.68394. Okay, now you see, compare with this value, only with one significant. Okay, because this number can be approximated to 0.7, right? So this is not good enough, right? Okay, let's check by the Simpson's rule. By the Simpson's rule, then b minus a over 6, remember 6, 1 for 1. Okay, fa, f middle point, fb. Okay, fa we already know it is 1, right? b minus a is 1, or 1 over 6, right? Multiply 1 plus 4 times a plus b over 2. It is 1 over 2, right? 1 over 2 square. So 1 over 4. So minus 1 over 4 power for exponential function, right? Plus e power minus 1. Okay? And you can calculate it by 0.74718. Okay, now you see again, we have 2 significant digits. Yeah, you see? So again, we show the Simpson's rule is better than the trapezoidal rule. It's okay for you? So firstly, you should understand how to construct the numerical integration. We use interpolation, quadrature means we use interpolation polynomial Pn. We use Pnx to approximate fx, then we use the integral of Pn to approximate the exact integral. And then we can transform the integral of Pn by the linear combination of some function values fxk multiply coefficients ak. And we know each ak is the interval of Lkx, the Lagrange interpolation basic function, basic polynomial. Clear? And here I show you the Newton-Cotes formula, means we use equally spaced nodes. Okay? So we also show you at least several famous or popular formula. First is trapezoidal rule, right? You should remember b minus a over 2 multiply fa plus fb. Okay? And next, I show you the Simpson's rule, very famous rule, b minus a over 6, 1 for 1. Clear? 1 for 1. 2 endpoints and middle point. Okay? And you need to, of course, this is just to let you know. Okay? We also have Cotes rule. If it is necessary, you can check in some manual book. Okay? You can check the also other quadratures. Okay? And you should remember the weights are symmetric and satisfy the partition of unity. Okay? So you can practice by the examples. Okay.